We will continue with our discussion of turbulent flow. In the previous video, we stopped with this equation. This is the equation for the u momentum. On the left-hand side, we have rho u squared. This is the time average quantity. This is what we would measure as the mean flow velocity. On the right-hand side, the same rho u squared show up as rho u prime squared, which is the transport of the u momentum, not by the organized velocity u, but by some turbulent eddies. So this is, we call it a Reynolds stress because it appears on the right-hand side, just like the molecular viscous stresses appear on the right side. We know how to model the molecular stresses, but we don't know how to model the Reynolds stresses yet. Same thing happens with rho uv. We get an organized component rho uv to the left side, fluctuating component rho u prime v prime time average to the right side. In the case of energy, you'll have rho times u times cpt on the left hand side. You'll have a rho cp times u prime t prime on the right hand side. This is the turbulent transport of heat. So for example, when you fan a fluid creating eddies, then you may be using it to carry a hot part of the fluid to the cold part of the region and vice versa. So this is what happens in turbulent flow. Eddies do the job of transporting momentum and also energy in addition to the molecular processes. The molecular processes are very small, very weak, very slow. So very often turbulent flow helps transport the material, mass, momentum, and energy very efficiently. So now we are going to look at flow over a flat plate. This was studied by Prandtl. It's the simplest of external flow problems. So very often this is where we start our discussion of turbulent flow. If you're doing experimental studies, you start with a flat plate before you go to airfoil or a wing or something more complicated. So ever since Prandtl started looking at it in the early 20th century, there have been thousands of databases that are available. They have detailed velocity fields, fluctuating velocity, time average velocity, you name it. Therefore, if you're developing a turbulence model, also sometimes called a turbulent closure, for modeling the Reynolds stress terms discussed in the previous slide, then such flows are very, very valuable, very, very useful. So we are going to work with a flow over a flat plate for the rest of this particular sequence of slides. As I mentioned to you, Viscous came along in 1877 before Prandtl started looking at turbulent flows, and probably contemporary to Reynolds, who was looking at the turbulent flow in a pipe. So what Viscous said was, let's say in molecular diffusion, molecular mixing, stress is proportional to strain rate or the velocity gradient, like Newton did and also Stokes did. So this is what happens in laminar flow. So Viscous said, I'm going to just replace this molecular viscosity with an eddy viscosity. So there used to be a rho here. You can put a rho here. Where is the rho? If you look up here, there's a rho here, but rho is not physically known. We don't need to model it, so we are only modeling this part of it. So that part is modeled as an eddy viscosity times velocity gradient. Molecular viscosity, eddy viscosity. Eddy viscosity, by the way, has got the dimensions of meter squared over second. So just like a kinematic viscosity, nu has got a meter squared over second type of a unit. So this reduces the turbulence modeling to just finding this one quantity. Unfortunately, it's not a constant. It varies from point to point to point. We just need to find that function. Once you know that function, you could stick it in here just like we are putting the molecular viscosity. So in a CFD computer program like a Fluent, they will first compute this eddy viscosity, then they will multiply by the mean flow velocity gradient, just as We take the molecular viscosity multiplied by the mean flow velocity gradient. As simple as that. So the problem becomes, how do I find this eddy viscosity, nu t? Boosness didn't give any idea. He kind of stopped at that point. So Prandtl, when he started looking at the flow over a flat plate in 1925, almost 48 years later, was one who came up with an eddy viscosity model. There were a couple of constants in his model, which Prandtl was struggling to find what it is. His nemesis, Theodor von Karman, he was in his lab. He came from Hungary, I believe, and he worked in Prandtl's lab. He took all the experimental data Prandtl had, curve fitted it, and came up with the empirical constant, as I will show later. Later on, Van Dries in Caltech, Prandtl von Karman's student at Caltech, further improved the model near the wall. Then around 1960, two engineers at Douglas Aircraft Company in Long Beach, currently it's called a Boeing aircraft in Long Beach, before that it was a McDonnell Douglas aircraft in Long Beach, they developed a more general turbulent model for turbulent flow over airfoils, over a flat plate, and so forth. So this is a long lineage. All of it starts with 1877, when Boosness came up with this eddy viscosity concept, Prandtl. Then 1960 is where the technology kind of matured. Now we are going to divide the turbulent flow in the flat plate into different regions. I'm going to walk through each region. We will just first quickly say what these are. One of them is very, very close to the wall, where you neglect the eddy viscosity because those eddies cannot survive because of the viscous friction at the wall. So only the molecular diffusion exists. So in the very, very close to the wall, we assume the flow is laminar. Only laminar diffusion exists. Then there is a small buffer region just above this viscous sublayer, where you have the viscous diffusion, molecular diffusion, and small scale eddies both exist. Then an outer, slightly next layer is called an inertial layer, where the viscous diffusion is weak, so we can neglect it. Only the eddies exist. Finally, you have an outer layer, which is between the inertial sub-layer and outer potential layer, called the defect layer. So we're going to walk through these regions one by one in our discussion. So I'm going to show the velocity profile. This is the velocity profile. If you plot it in just a physical scale, it'll look like this. And this is a y, distance from the wall. This is the velocity profile. Notice that the velocity gradient near the wall is very, very high, very steep gradient. That means the velocity goes from 0 meter per second to some finite value within a micrometer or so. So you have a very, very high stress. So turbulent flow is a very high shear stress. Why is it so high here? Because those eddies are bringing the high velocity flow from out here. It's bringing it down all the way to the bottom, making this velocity very fast. Likewise, they take this low velocity flow near the wall. Same eddies will transport out there to making this region as relatively slow flowing. So we call that the defect layer. So viscous sub-layer is very, very close to the wall. Inertial buffer layer is the next layer, inertial layer, and the defect layer. Now this is the same velocity profile as shown in this curve, except I have made this distance equal to logarithm of a quantity called y plus, which we will define later. This is the actual u velocity non-dimensionalized by some quantity to make it a u plus. Again, we will show you how you non-dimensionalize it. Whenever you non-dimensionalize it, you get a universal curve like this. That's the power of non-dimensionalization. That's why we deal with the Reynolds number, Mach number, We want to keep everything non-dimensional if at all possible. Now, you see that in this region, it's a relatively a straight line. And there are two constants floating about. So Prandtl had already gotten this red line as experimental data, but he didn't know what these two constants was. Von Karman took his data, curve fitted it, and empirically came up with the slope, which is 1 over kappa, and the intercept, which is the letter b, with the y-axis. So we will see those things later in our discussions. So let's talk about the viscous sublayer, which is the lowest level layer close to the wall. In this region, we only have molecular viscosity. Turbulent eddies do not exist because of the viscosity friction at the wall. They get slowed down, damped out, they turn into heat. So turbulent fluctuations get converted into heat, they disappear. So you only have a molecular diffusion that survives. So in this region, the U momentum equation greatly simplifies as shown in the next slide. Notice that this is our momentum equation, U momentum equation, which we wrote earlier. These are our Reynolds stress terms that we have to model. We are showing it in 2 dimensions, x and y. This should be y, not x. Let me go ahead and fix it. This should be y. Okay, so this is the momentum equation we saw before. Since we are very close to the wall, Prandtl said I'm going to neglect the U, which is very slow flowing velocity, V, very slow flowing velocity. When you first start modeling, you have to start somewhere. You can't just keep every term. You try to ignore or neglect the terms which you think are not important. Then, later on you can come back and fix it. So this is what Prandtl did. I'm going to neglect this term because U is small. I'm going to neglect this term because V is small. I'm going to neglect this term because it's a flat plate. Potential flow is uniform over the flat plate. Therefore, the Bernoulli equation says the pressure is uniform in the edge of the boundary layer. Since dP dy is 0, pressure is not changing across the boundary layer. That means everywhere the pressure is constant. So he neglected this. In the boundary layer theory, we neglect the x diffusion terms and x diffusion terms. The order of magnitude analysis, so this term went away. So the only term you are left over with is the y term, d by dy of tau xy, and then the eddy terms. Now the eddy terms were neglected in the viscous sublayer because the eddies because of the wall friction, they get damped out, they turn into heat. So the only survivor is this sole term. So it becomes like this. Extremely simple form. It can be now integrated very simply. So what we find is that the tau xy is a constant in the viscous sublayer. So if you have somehow a way of measuring the gradient at the wall and compute the tau wall, that constant is nothing more than the tau at the wall. Now we know from Stokes relations that tau xy is mu times du dy plus dv dx equal to tau xy. Again, using the boundary layer hypothesis, things vary slowly in the x direction, things vary rapidly in the y direction. Therefore, dv dx is neglected. You may remember from the boundary layer analysis, v is of the order of 1 over square root of Reynolds number. So it's a small quantity, so we neglect this term. So you only get mu du dy equal to 0, tau xy, tau at the wall. If you integrate it, you get uxy equal to tau at the wall, mu over y. it's a linear velocity profile. So very close to the wall, you get a linear velocity profile in the viscous sublayer. This is a dimensional quantity. So we want to non-dimensionalize it and come up with some kind of a universal way of describing all boundary layer flows over all flat plates, all experimental data, everyone's work. So what you have to do is you have to non-dimensionalize somehow every dimensional term in here. So this is what Prandtl did. He said, I'm going to call this tau wall equal to, it's got a units of density times the velocity squared. So he said, I'm going to represent tau wall as density times a quantity called u tau squared. U tau is called a friction velocity or a wall friction velocity. So now you could write tau wall as rho u tau squared. We have a molecular viscosity in the denominator. Mu over rho is kinematic viscosity, which is nu. Now you group velocity terms to one side, bring one of the u taus to the other side, so that the left side becomes non-dimensional. It then follows the right-hand side should also be non-dimensional. So now you have a non-dimensional quantity and a non-dimensional quantity. So u normalized by the friction velocity is called u plus. Y non-dimensionalized by y times the friction velocity by kinematic viscosity is called y plus. So you get a nice linear velocity profile in that regime. So this is the viscous sublayer that Prandtl model or Prandtl hypothesized. So indeed, when you do the experimental data, when you take experimental data and measure in this region, this is that y plus, which we defined, is y times u tau over nu, where u tau is that friction velocity. This is u over u tau, which is u plus. And indeed, you get a linear profile. But if you make this log of y, you get a nonlinear curve. So you could curve fit in this region here. So this is the first region that Prandtl came up with. Then he said, let's take a look at the buffer region. Here you have a viscous effects are present, and you have the eddy effects are present. Both are present here. Right here, the molecular diffusion dominates. In the inertial region, the eddies dominate. In this in-between region, both the molecular diffusion and the eddy effects both are important. Prandtl really didn't know how to model it. He said, I'm just going to pair this region with my favorite French curve. Okay, he called it a buffer region. Okay, so he did not mathematically model it, analytically tackle it. So what he did was he said, okay, this is my equation. Again, the second term should be dy. So let me fix it. Apologize. So this should be dy. So again, he said in the buffer layer, U and V are very small. There's no pressure gradient because this is flat plate. There's a molecular diffusion in the streamwise direction is neglected by boundary layer hypothesis. Therefore, the eddy diffusion in the streamwise direction is also eliminated by the same boundary layer hypothesis. Then you have the two terms survive. Molecular diffusion and eddy diffusion both. So in the buffer layer, you get an equation like this. If you integrate it one time, you get mu du dy minus rho u prime v prime squared. This should be a constant. So if you go close to the wall, that constant is tau wall. Therefore, this is the behavior of the buffer layer. So Prandtl said the laminar diffusion exists, and so does the turbulent eddy-based mixing. Laminar-based molecular mixing and eddy mixing both exist. They actually complement each other so that their net sum equals the pure molecular mixing at the wall. Mu times du dy at the wall. So this is what he postulated about the buffer layer. But he couldn't go any farther. He said, I'm going to just pare the region between the laminar region, which is the viscous sub-layer, and the layer above it, which is called the inertial layer, this buffer layer. I'm just going to curve fit it somehow. So he went to the inertial layer, which is above the buffer layer. There, the laminar viscous stresses we saw in this are neglected. So you only keep this term because the molecular diffusion is an order of magnitude slower, weaker than the eddy diffusion. So he only kept this term equal to tau at the wall. So in inertial region, the laminar viscous stresses are neglected. The Reynolds stress is constant and equals tau at the wall. Okay, so Reynolds stress is constant in the region, equal to tau at the wall. That's what happens in the inertial layer. Inertia means inertial region means a velocity gradient are important. Eddies are important. So again, several terms disappear. Again, the second term should be d by dy. Should be y. Let's go ahead and save it before I forget. Okay. So he came up with an equation that became something like this. It's a very nice equation. You can analytically integrate it once. Then you basically get the Reynolds stress in the inertial layer equals tau at the wall, as we saw earlier. If you put in the Boosness hypothesis, the Reynolds stress is density times an eddy viscosity, which we don't know what it is, times the velocity gradient equal to tau at the wall. So Prandtl was the very first person who developed an eddy viscosity model, this new tau, for flow over a flat plate. So we're going to stop at this point and continue with what happens in the inertial sublayer in our next video.